Welcome back everyone to another geoscience data tutorial. Today we are building an end-to-end lithology classifier that combines core imagery with geochemical data. Think of this as a miniature version of what industrial core scanning systems try to do. But this is reproducible with no black boxes and everything transparent. You can download the Jupyter notebook from my GitHub. In the real world, this kind of classifier sits on the core scanning line and pays for itself by tuning pictures and a few quick assays into decisions that can move dollars. So, for example, distinguishing between ore or waste, feed or stockpile, or even in metallurgy, easy or hard to float in flotations. Think of a nickel copper projects. We're telling high sulfide ultramafics from barren gabbro or altered ultramafics. These are all changes that blend the reagent belts and the recovery you can promise. So a production setup ingests core photos, line everything up by depth, and pushes the lithology tags with a confidence score straight into the short-term plannings. In this tutorial, we strip that down to 3 simple buckets: mafic, ultramafic, and felsic. So you can see the impact without getting buried in 40 labels and a dozen edge cases. The same idea, but fewer moving parts. So let's formulate a problem first. So when the ore feed keeps changing, the plants keep wobbling. So what's happening here is that sometimes the feed is high in sulfide, sometimes it's low, or the rock mix changes, ultramafic, mafic, felsic, different alterations. When the feed shifts, your frost changes, entrainment changes, and recoveries go up and down. So this hurts because it lowered the overall recovery, wastes the reagents, and also extra operator headaches and unstable performances. So what the industry keeps saying, because it's really true, keep the head grade steady, pre-concentrate early so the plant sees less variability, or use sensor-based sorting and better front-end classification to smooth the feed and cut the costs. So changes in feed grades shifts flotation behavior, frost stability, entrainment, and recovery. They're all moving. Water chemistry can make those shifts even bigger. And if your feed bounces, your plants bounces. So part of the mess starts upstreams. Manual core logging isn't perfectly consistent. Different people, different shifts, different results. That's why automation is showing up here to tighten consistency. How you will teach, I'm going to teach this is to use 3 buckets for rock types: ultramafic, mafic, felsic, or you can just call it A, B, or C. And the exact names here doesn't matter. We are teaching the workflow. So smooth the feed first, then the plant behaves well. Stabilize head grades, use pre-concentration, sort early, and get consistent logging. So what you do here is to grab a quick photo of each interval stockpile and get a fast, for example, nickel, copper, iron, sulfur as a lab batch, or even with handheld XRF. They're all appropriate. The model classifies a material into routine classes that actually matter operationally. High sulfide melt feed versus low sulfide blend, or waste or stockpiles. And not just pretty lithology codes that I explained. You can change the codes. So you blend and sort accordingly so the plant sees a steadier head grade and sulfide contents. So, but why it works? So images catch texture, tone that's correlate with sulfide modes, massive net texture or disseminated sulfides. And chemistry anchors decisions numerically. For example, the sulfur percent, the mass of sulfide, or your nickel copper. Also, iron helps to separate oxide-rich chunks. So if you're using these two signals, both signals are good enough for pre-classify ore, so you can route it better. That's exactly the premise behind sensor-based pre-concentration. Remove waste early and reduce feed variability to the plant. What the notebook does step by step: first loads data with geochemistry, with sample ID, lithology, everything. Then is visual sanity checks that shows images so you can catch weird lightings, rotated trays, or mislabeled files before training anything. PCA and geochemistry that standardize elements, project them to PC1, PC2, and plot by lithology. Then there is handcrafted image features on textures, colors, for example, GLCM contracts, homogeneity, and also entropy captures graininess of fabric. For color is a 48-bin RGB histogram that actually captures oxidation tones and mineral proportions. We write a file, a CSV file, so you can have a clean, auditable table per sample. Then we'll go to the CNN baseline on images. Tiny cross CNN actually learns edges, textures, and gives you a train validation accuracy curve. And finally, a hybrid classifier that merges chemistry and image features and trains a random forest. The output is a classification report, a confusion matrix, and a top feature importances. Okay, in the first step, we import pandas and loads our table from geochemistry.csv into the data frame, and we call it DF, data frame, and this assumes the CSV is in the current working directory, and I use df.head to quickly confirm the first few rows and check that if the columns like sample ID and lithology exists. Here we connect rows to images by file name. Each image is named sample ID.png inside the sample underline core underline images. And I did a quick sanity check. Then for a broader scan, I created a 3x3 grid for images. Then is encoding labels. First, the imports, pandas for tables, matplotlib and seaborn for plotting, and scikit-learn that we grab for the standard scaler and PCA. I load geochemistry.csv into the data frame. We have done it before here. I assign as geochem underline pass. Then I map the text lithology to integers with the dictionary. That lithology underline code is optional but handy for machine learning. I keep the original strings columns so legends stay readable. Here I pick 4 geochemical features as columns and extract them as a numpy array X. PCA cares about scale, so I standardize with standard scaler. So each columns become mean 0, variance 1, and that prevents, say, nickel in ppm from bullying sulfur in percent. Then I create a PCA object with n component 2 and fit transform the scaled matrix. The results, the components is our data rotated into the direction of maximum variance. So I stash the first 2 axes as PC1 and PC2 back into the data frame for easy plotting. So I plot PCA map colored by lithology. I open an 8x6 figure and use Seaborn's scatter plot to draw PC1 versus PC2. And these are some plot features. The hue is lithology colors point by class, which lets us visually check separation. Palettes is set to is a gentle categorical palette, and S equals 80 here bumps point sizes, and black edge helps contrast on light backgrounds. Each point on this scatter plot is a core sample. The color shows its lithology: green for felsic, orange for mafic, and purple for ultramafic. The axes are principal components. PC1 is on the x-axis, PC2 on the y-axis. These aren't raw elements. They are a combination of elements. For example, nickel, copper, iron, whatever you chosen, that captures the strongest pattern in the data sets after we standardize everything. So points near to the center are close to the overall average chemistry. Points farther out are more unusual mixes of those few elements. If classes separates cleanly by color, it means those elements alone can distinguish the lithologies well. Here we see partial overlap, which is realistic. Some mafic felsic samples share similar element signatures, and a few outliers here are chemically extreme. And those outliers are either interesting geology or data check waiting that to be happened. So remember that PCA didn't use the labels when computing these axes. The colors are just to help our eyes judge the separation. Also, because we scaled the inputs, the axes are in standard deviation units. If you want more insights, add the variance percentages to the axis label and draw a biplot to show which elements drive PC1 and PC2. You can see my other videos to know how to do it. PCA was a quick X-ray for the geochemistry only, but after that you will build features from images and then save them to a tidy CSV, and then fed the combined data into a classifier such as random forest to actually predict stuff. So in this script, we have defined a function here that turns images into numbers. For each PNG in sample underline core underline images, we compute 3 texture metrics from the gray level co-occurrences matrix and a compact color histogram from the RGB channels. The output is a CSV ready for clustering or classifiers. Here, after importing libraries, we build a GLCM. So grain comatrix here count how often gray level I sits next to J. Distance here as 1, use immediate neighbors. Angle 0, look horizontally. Level is 255, treat grayscale from 0 to 255 as discrete levels. Symmetric, here's true, that a mirror counts for I and J and I. Normed here also true, that turns counts into probability. Then we pull texture measures. So contrasts, 0, 0, compute contrasts for the single distance or angle, and pick the first cell because we passed 1 distance and 1 angle. Homogeneity 0, 0, do the same for homogeneity. Compute entropy and also the MP sum GLCM. Here apply Shannon entropy to GLCM probability. Then we color histogram features. Extract each channels. 0 is red, 1 green, and 2 is blue. MP.histogram 16 bin, range from 0 to 255. It counts how many pixels falls into these 16 intensity bins. concatenate red plus green plus blue to a 48 length vector, and finally normalize so the histogram sums to 1. And this makes the features scale-free across different image sizes. Then package the features into a flat dictionary, processing the entire folder, and finally run and save it. Now is the time to map each image into a lithology label from the CSV file, build a small CNN, train it, and plot the accuracy. In this code block here, we load labels and images and then encode them and then a split. So read the CSV and index by sample ID for fast lookups. Resize each images to 64 by 64 and scale pixels to 0.1 by dividing by 255. Small, fast, good enough for the demo, and you can bump it later. Collect images in X and their strings labels in Y, then convert to NumPy arrays. Map readable classes to integers for the model, and one hot encode to shape the number of samples 3 because we'll use softmax with 3 classes. Then we split 80-20 for train test using a fixed seed for reproducibility. This is the CNN architecture. So conv2d is 32 3x3, learns 32 small edge or texture filters. Max pooling 2x2 halves spatial size, keeps the strongest responses and reduces parameters. Second conv pool learns high level patterns, flatten, convert feature maps to the one-dimension vector. Dropout 0.5 is for regularization, randomly drops half of the units each step to reduce overfitting. And dense 48 here is a nonlinear mixing layer, and dense 3 softmaxes outputs class probability that sum to 1. And these settings are actually baseline. So this is a classic plot that shows the CNN learns fast. So blue is the train accuracy, orange is validation accuracy. The training curve should rise, validation curve should ideally rise and then plateaus. If training is much greater than validation, you're overfitting, so you need to add augmentation, more dropout or early stopping. If both are flat or low, the model is underfitting, dependent on raise input sizes or add better features. So here we have a rapid lift from 0.3 to 0.8 by epoch 3 to 4, and both curves converge to 1 by epoch 7 to 8. So what you're seeing is the model accuracy per epoch for the training set. Two things matter here. The validation curve tracking the training curve, that means we don't see classic overfitting. Hitting at 1 on validation can be either legitimate because the classes are visually distinct and the dataset is clean, or it can be a sign of an easy split or even leakage. So the takeaway is that the model learns useful visual features very quickly and generalizes well on this split. Now let's match the rocks chemistry with what the pixels look like. So the goal here is to classify lithology using geochemistry plus image features. So our inputs is geochemistry.csv is all the elements that we have, lithology, and also the other CSV file, that image underline features.csv, which is a color histograms plus GLCM the contrast, homogeneity, and entropy. So the model we are using is a random forest classifier, and our outputs is accuracy, confusion matrix, and top features. So actually we are merging numeric geochemistry with cheap but useful image descriptions. Random forest is robust, needs little tuning, and handles mixed scales without drama. So the first step here is read both tables and inner join on sample ID. Any sample missing in either file is dropped by the merge, and that's intentional, otherwise you would be training with half of your story. Map labels to integers for the classifier. So the feature set is 4 geochemistry columns plus image features, which is 48 histogram bins and 3 GLCM stats. We select columns for the merge table, so every row aligns with its target. Forests don't require scaling, bless them. 80-20 split with a fixed seed for reproducibility. Random forest with 100 trees is a solid baseline, which reduces variances by averaging many decorrelated decision trees. If your class are imbalanced, add class underline weight to balanced or stratified the split. This block here is for classification report that gives precision, recall, and F1 per class, and confusion matrix that tells you who's getting confused with whom. This code block gives us how much each feature reduces the impurity across the forest. This is a classification report. The overall accuracy is 1 on 20 test samples. The confusion matrix, as you can see, is a perfect diagonal. Every test sample was classified correctly. Precision and recall of 1. That means there were no false positives or no false negatives for any class on this split. The confusion matrix is perfect diagonal, which is the simplest way to see none of the classes are getting mixed up. The caveat is that the test set is small here. It's only 20 samples, so 1 or 2 mistakes would swing the percentages a lot. This result is excellent here, but we still need to rule out data leakage and confirm with cross-validation. The bar chart of top 15 feature importances here. All shown features are hist underline bins from the RGB color histograms. No geochemical variables or GLCM stats appear at the top 15 in this run. The forest says color histogram bins carry most of the predictive powers here. So each histogram is one intensity bin from RG or B, and together they captures a broad color balance. That lines up actually with geology, the felsic versus mafic versus ultramafic cores. These often differ in an overall tone and oxidation staining. This is the entire workflow, but there are some caveats. So we may have data leakage risks. So if multiple photos from the same box land in both train and test, you will get some fake numbers. Use group aware splits by drill holes or box trays. Small test sets, so perfect scores on 20 samples are cute, but not conclusive. Use stratify K-fold CV and report variance. Lighting and drift, so color features are sensitive to camera and lighting. Standardize the capture or color calibrate. The label quality is important. If lithology code are inconsistent, the model will faithfully learn your inconsistency. So, garbage in, elegant garbage out. This workflow is transparent, reproducible, and totally customizable for other datasets or projects. You can find the Jupyter notebook of this tutorial on my GitHub. The notebook is compact, explainable pipeline that turns core photos plus basic chemistry into something operational. If you found this helpful, give it a like, leave a comment with questions, and don't forget to subscribe for more geoscience and data tutorial.